Hi, my name is Jackie. Welcome to my TED Talk. I'm going to talk to you today about Sudoku, Latin squares, and a game of my own invention called Modoku. And you'll find out why later. So we all know the game Sudoku. You can play it in newspapers, on your phone, computer. You can even get those little books at the register in grocery stores. The rules are very simple. You have the numbers 1 through 9 that have to appear exactly once in each row, in each column, and each subblock. But did you know that a Sudoku grid is actually a mathematical concept called a Latin square? A Latin square can be defined as an n by n array containing the symbols 1 through n in such a way that each symbol occurs once in each row and once in each column of the array. Simply put, a Latin square can be as shown on the screen in Skittles, where every color is going to show up exactly once in each column and each row. For example, if we took away most of the Skittles except for those contained in the topmost row and the leftmost column, we see that the red Skittle appears only in that top corner where the two meet, versus the yellow or the green, orange, and purple Skittles, where they can all appear in both the top row and the left column because they never meet anywhere else. A Latin square got its name from Leonhard Euler, who used Latin symbols in his first iterations of the Latin square. However, as I have shown before in both the Sudoku and my Skittle iteration of this grid system, it does not have to simply be left to symbols alone. Latin squares are also used by farmers to test new soil. Adapting a similar pattern to test where their produce will grow the best and in which areas, farmers can guarantee their best products by adapting this mathematical concept. It's easy to see from these examples where the idea for Sudoku originated. But what would happen if a Sudoku grid wasn't a Latin square? Could a game still be easily made if it only had, let's say, a 3 by 9 grid system instead of the traditional 9 by 9? Well, each row and block can still have the same rule where it needs to contain the numbers 1 through 9 exactly once, but a new rule is needed for the columns. Let's try this. Each column must add up to some number k such that when we divide it by the number of elements in the column, every column will have the same remainder. So, for example, we'll look at this 3 by 9 grid, and we can see when we add the numbers 1, 4, and 7 in the leftmost column, they add up to 12. Going to the next column, 2, 5, and 8 will add up to 15, and 3, 6, and 9 will add up to 18. Well, there are 3 elements in each column, so dividing 12, 15, and 18 by 3, we will have a perfect division for each, meaning none of them will have a remainder. So at least for this grid, our new rule holds. They all have a remainder of 0, therefore satisfying the conditions of the column rule. Now let's take a look at this grid. 2 plus 4 plus 7 is equal to 13. 3 plus 5 plus 8 is 16. And 1 plus 6 plus 9 is also 16. When dividing these all by 3, you have a remainder of 1, since subtracting 1 from each of the sums gives you a multiple of 3. For example, 13 minus 1 is 12, and 16 minus 1 is 15. This is a mathematical concept called a module sum, and it is going to be key for the rest of this presentation. So we can see that, at least through these two examples, the rule seems to hold for a 3 by 9. But what would happen if we were to expand that grid? Let's say to any general size. Does this equality rule still hold? Well, let's consider any and all n by n square grids. So it would include 2 by 4s, 3 by 9s, 4 by 16s, and so on and so forth. Again, by our rules, we know each row and each block will contain the elements 1 through n squared. And by design, we know each column will contain n number of elements, like so. Okay. To represent each possible sub-row of each block, we can partition the list of elements 1 through n squared such that we have p sub k equal to kn plus 1, kn plus 2, all the way through kn plus n for any k containing the elements 0, 1, 2, all the way through n minus 1. Put simply, p sub 0 would contain 1 through n elements, p sub 1 would contain n plus 1 through 2n elements, p sub 2 would contain n 2n plus 1 through 3n elements, and so on until the last k is reached, giving us p sub n minus 1 containing n minus 1 times n plus 1 all the way through n squared elements. Moreover, we can apply a cyclic permutation to each p sub k to achieve even more possible grids. Let sigma represent a single cycle rotation of each element in p sub k. For instance, if we apply sigma to p sub 0, now that's going to be equal to sigma, the list 1 through n, and then applying that sigma, we achieve 2, 3, all the way to n, 1. We can apply sigma again to our new p sub 0 list and obtain the order 3, 4, all the way to n, 1, 2. In fact, we can apply sigma n minus 1 times before reaching our original list of p sub 0 equaling 1 through n. Lastly, to achieve all possible working grid combinations, we must also shift our ordered list of p sub x, like so. In the end, we should have a p sub x arranged matrix as such. Combining every possible cyclic rotation of sigma to our p sub k matrix we have created, we achieve the following matrix. And by construction, each column of our matrix should represent each possible block of our n by n squared matrix. So to verify our new rule works for any given block, we'll test an arbitrary block J. By our construction of p sub k, we can see the block can be written like so. Since p sub k equals kn plus 1, kn plus 2, all the way to kn plus n. Applying our rule of mod n to each row yields the following matrix, since any element multiplied by n when modded by n will have a remainder of 0. Now we can see for each column, the sum of the entries is 1 plus 2 plus all the way to plus n mod n, which we can simplify to be n times n plus 1 over 2 mod n. And since each column represents the columns of a single block in our n by n squared grid, we can see that they are all equal to each other, satisfying our new rule. So yes, this equality rule holds for any n by n square possible grid. A more in-depth explanation of this proof and other possible new rules can be found within my paper. Please enjoy it and have fun playing my new game, Modoku.